that was very interesting story. So I am very happy that you mentioned that our effort is rewarding. Hi. Today, I would like to start by thanking organizers for giving me the opportunity to talk to you about our story, and also for great job for preparing this symposium. I am from Tohoku University. Let me share. It came. Sorry, this is summary. Can you see my slide? No?
No.
Oh, how should I share? Okay. 画面共有。
That's better.
Yeah?
That's
Now,
best.
yeah. I'm
Good.
very sorry. I lost how to get into this conference, and I forgot to press X, so I could not get that. So I am sorry to lose some minutes, but I would like to talk to you today, X-ray diffraction study of nano-confined liquid. First, I can introduce you my colleagues. This is a collaboration of Professor Yagi's group of Spring 8. And these two people are working hard on the project. Masashi Mizukami, my colleague, and Yagi's colleague of Noboru Ota. They are the key persons for this work. And today I would like to introduce you briefly background of our work about surface forces measurement, confined liquid, XRD of confined liquid, and several topics we studied recently. I don't know how many of you are familiar with surface forces measurement. This is even developed before atomic force microscope, but now that the FM is much more familiar. We did measure interaction force using spring balance and obtain interaction force profiles, which is interaction potential profiles, so that the repulsion is plotted positive and attraction in negative and distances. So this is, we get so interaction profile. So this is considered best method for studying origin of interaction forces. But often that we do not know the origin so clearly. So I said that this is a good way to study sometimes interface, because we have, if interaction changes, that means something changed at the interface between the solid and liquid. And this is usually very difficult to study such interfaces very at molecular level. Also, we can take advantage of precise determination of distance by controlling surface separation. And also lateral force can be studied. And so these are something we take advantage for X-ray diffraction too. The conventional SFA surface force apparatus is shown in right-hand side. We have large surface. If you only know the FM, this is very different. We have a large spring of several centimeters, and this disc, which is usually glued, the substrate is usually glued on such disc, which has a diameter of 10 millimeters. So that, however, the distance resolution of surface gap is very precise of 0.1 nanometer. And the contact area is usually about 30 micrometer. So this is very large in XY plane, but in very precise in a height direction. So this is very unique setting. So I think we can bridge macro or mesoscale phenomena with none. Actually, there are not so many people doing this kind of study. But I feel this is very important because elucidation of interaction is essential for material science. Everybody will agree, but not so many methods compared to structure characterization. So this is generally very important and essential. And also characterization of solid-liquid interface is important in research of advanced materials. And complex matters, real matters can't be fully understood by a single molecular measurement, which is the most idealistic probably case for AFM. And the study of weak interaction is possible because of large surface area. And gradually, when we accumulate the knowledge about interaction, I started to feel combining these two information is actually we are making kind of accumulating knowledge about interaction, origin of interaction. However, conventional SFA surface force apparatus is not always enough for everything if we want to study materials. So we do sufficient instrumentation, like we constructed a twin pass SFA for opaque samples. This is only, actually, I think that only one SFA for opaque samples, practically. And we, for lateral force measurement, we developed resonance measurement. And which we, using this, we study intensively the property of confined liquid. Also, surface other than mica should be used. So we do make quite effort for preparing flat and smooth surface of various materials. And the evaluation of interaction forces is also very important. So we do complementary characterization, including X-ray diffraction. And models and simulation are important. Also, we recently developed a device for precise temperature control. So that let me shift to the confined liquid topics of confined liquid. The confined liquid, besides probably the what is, excuse me, the water structure, suddenly I forgot English name. The solvation of by water is was not so well known until this study was done in about now about 40 years ago. The Roger Fong and Jacobus HB found that when they confined OMCTS, very spherical molecule in a narrow gap, there is a such oscillation in their forces, which corresponded to layered structure of molecules. And that is a very new finding at that time. And we continue such research using our device of resonance measurement, which is very sensitive to the change in property of confined liquid, because we use resonance signal of this top unit, which hanged by two springs. So we oscillated, and at the resonance frequency, the peak is very large, so that the property such as viscosity, when viscosity changes, the peak, resonance peak decrease. And the frequency and amplitude of such resonance peaks are very sensitive to other structuring and viscosity and friction and rigidity, such properties. So we use such techniques for studying confined liquid. And there are many interesting phenomena we could observe using such device. The right-hand side figure shows examples of such case. We confined liquid crystal. molecules between a gap and studied their viscosity using some models. Which this is the damping parameter correspond to the viscosity, and at the distances below 20 nanometer, viscosity started to increase like this. Then when we applied electric field, the orientation of liquid crystal changed to such a way, and viscosity, so that viscosity increases for such lateral motion. But at the distances below 10 nanometer, the two values started to coincide. That means that the electric field cannot change the orientation of liquid crystal at such narrow gap. So this is the first observation of such confinement effect. But naturally, then we wanted to know the structure of such cases. This is just a model to show that we can calculate viscous parameter or elasticity parameter using model. So then we became interested in an earlier attempt of using X-ray diffraction in SFA surface forces apparatus. The very early attempt of X-ray diffraction study using SFA was done by the group of Jacob Strachvili with his colleagues in Santa Barbara. I cannot read so well, but it's Isaac and Safin. They used capillary tubes, crossed capillary tubes, or the discs this is a disc same as identical as SFA, identical one for SFA as SFA, but with holes at the middle, and did the X-ray diffraction study and studied the shear-induced orientation of liquid crystal. But their case, they only can study distances about 400 nanometer and above. And if you remember my data, the confinement effect appears at distances smaller than 20 nanometer. So this is not enough sufficient for studying confined liquid. And we believe this is the first example of X-ray diffraction study from nano meter thickness liquid. We took very same setting as researchability group, but tried to really accumulate signals and improve the signals. But at that time, we do not know how to regulate different gaps in a small distance. So we did two cases at 2 micrometer and 2 nanometer. This is a very compressed hard wall thickness. But we could obtain the scattering spot like this. But this actually relaxed to no clear X-ray diffraction spot after 100 minutes. But anyway, this is the signal corresponding to the longer molecular length like this. And also at 2 micrometer, we have seen that also this short length corresponding to 0.43 nanometer, very small, small peak. But this peak is very clear, and this peak is very clear for 2 nanometer thickness field. Then we wanted to regulate better the distance. Now we do it with a feedback system, and most studied system we have done so far is ionic liquid. Ionic liquid has attractive property such as low vapor pressure, non-flammability, and stability, high ion conductivity. Therefore, they are expected to be used for many applications like electrolyte, solvent, and lubricant, etc. So that we wanted to know most of the application requires how the information about how they behave in a confined in small spaces. So we wanted to study them. If we studied two kinds of ionic liquid, which has the same cation and different anion, shown here. If we study normal force, there is a quite clear oscillation, which means layering. They have layered structure. But these two ionic liquid did not show so quite different behavior, although that with smaller combination shows shorter oscillation. However, if we look at this resonance peaks, this is a frequency and resonance amplitude. And when we change distance, peak changes from this frequency to this frequency. And so if this peak increases, that means we have larger viscous, we see that the viscosity of liquid is larger and friction is large. Traction between surface is large. But this means that there is low friction and lubrication properties very well here. And if we plot the viscosity, effective viscosity in terms of distance, although bulk viscosity is larger here, at confined situation below 10 nanometer, viscosity increase several orders of magnitude, but this shows a smaller viscosity increase, which is opposite to bulk values. So this kind of data shows that bulk measurement does not mean anything in a confined space. But why? Why this combination shows high viscosity and why this one is not? We did computer simulation with Alex Schulger's group, and the simulation shows very interesting behavior. In case of this larger cation, the cation and anion align alternatively. So the checkerboard like a organization with simulation indicated. And this BF4 minus case, that they same ions are organized in one layer and another ions, and this is alternate layer. So if you shear here, cation hit cation and anion hit anion, so this kind of shear mode is not favorable, so we see large friction. But this case, shear does not change structure so much so that we can move it smoothly. And we study X-ray diffraction from such systems using very thin silica sheet on mica. We could spatter such silica sheet on mica, and this is to avoid large background X-ray scattering. And the obtained signal for at 3 nanometer thickness film is shown here, which indicate such alternate alignment of ions. But in case of F4 minus, this peak up disappears. So this structure agreed with this such alternate layering of different ions. So we can show that such X-ray diffraction is very effective for characterizing confined liquid, and obtained results supports a different structure for different ionic liquid proposed by our simulation studies. So if the ions are aligned in such a way, the distance between ions are quite different depending on the cases, so that we do not see any clear diffraction peak. But this case, because of very clear organization, we see the peak. And I can briefly show you that how we could study shear effect. And in this case, we studied H2CB liquid crystal between mica or silica using similar setting. In case of mica, we have seen that such short the peaks little bit wide, 22 degrees spread, 22 degrees diffraction spot. But in this case, we have seen that rings, so which correspond to such more organized structure between mica, because we know that liquid crystal align along the crystal axis of mica. But in the case of amorphous silica, we do not see that such alignment along a certain axis, so we see that ring. If we share such systems at confined state, we only see that very small change in diffraction spot and angle change of by 3 degrees. But if we share at very large gap, and if we narrow the gap, we can observe shear effect of such. Because I would like to keep some time, a little bit quick at the end, but in summary, our studies show that X-ray SFA can be efficiently used for obtaining structure of nano-confined liquid. This can afford the useful information to understand their properties, which are quite different from the bulk. And I can mention that other groups now using X-ray XFA, including Kekse's group. He used small angle X-ray, and Melgar's group of Max Planck for polymers in Mainz is using reflection mode. So I think now that we are quite able to study confined systems using X-ray SFA at molecular level. Thank you very much for your attention.